Electrical circuits is the topic of today. Electric circuits. This will be a review and a refresher from grade 9 for the most part. Basically, if you have a way of providing voltage, which is of course the force that moves electrons over a certain distance in a circuit, and you have what's called a load. The load is basically whatever it is that is in the circuit, the thing that you're trying to get some useful work out of. So for instance, here's some examples. You might have a light bulb. That could be a load on a circuit, right? You might have a heater. That could be a load. You might have a motor. All of the things that we use electricity to do, all of these could be what we call a load. So instead of being specific, we often just refer to the word load, which indicates something that the electric circuit is trying to accomplish, right? And of course, one thing that's in common with all of these different types of loads is that they provide resistance, which is they resist the flow of electrons. The electrons have to do work in order to make it through the load. And that work eventually shows up as the light from a light bulb, the heat from a heater, or the spinning of a motor, you see? So the electrons are moving through the circuit, and they're doing work because the voltage is providing force times distance, and the force times distance is work that's done on the electrons, right? And so the electrons are doing the work, but when the electrons pass through a load, they change that work or convert that work into a different form of energy, which could be light or heat or kinetic spinning, motion, all those things. The trick, of course, is that in order to make a circuit, you have to attach the voltage source and the load. So you need to have a wire or a conductor. So we have a conductor, and that's just a fancy name for a wire. Now, of course, it could be anything. Believe it or not, circuits in the real world, although 99% of the time they use wire, they don't all. In your car, the actual body of the car, the metal body of the car, can provide a portion of conductor for the circuit to flow through, for the electricity to flow through. The pipes in your house can actually contribute to electric circuits. And so there are lots of different things. As long as you're a conductor of some kind, then you can have electricity flow through you. A conductor, of course, offers very low resistance. The electrons can move freely through the wire. There's some resistance, but not very much. Now, the other key thing is that if I connect it like I've drawn, well, voltage provides force, and force is a vector. And that force is in a certain direction. So if the voltage is pushing the electrons through the wire this way, in this direction, well, clearly, once they get to the load, then everything piles up and they stop. And electric current has to continuously flow in order to keep the load doing its thing. So we must also provide a return path, which gets us back so that it's a circle, right? The word circuit comes from the word circle. And of course, you can't move against the way the current is going. If current tries to flow backwards this way, it's working against the voltage, which is trying to push it through the circuit. So that's why we need a circle shape, or at least not necessarily a circle, but a complete path, right? There has to be a complete path. And that path in most circuits is very complicated. It doesn't look like a nice, easy circle. But as we begin to study circuits, we will start off with circuits that are very simple and have very easy looking paths. All right. Now, of course, in grade 9, you would have learned that we use symbols when we're drawing these pictures. Instead of the picture that I drew, we use what's called schematic diagrams, or pictures that represent things. So what we might do in that picture is we might draw this, which represents what we call a battery. Right? And if you recall, each one of these little pairs of lines, a long line and a short line, that is what we call, that's what we call a cell. A cell. And a cell is a very tiny battery that has a negative and positive side. So the little short guy is the negative side, it looks like a negative sign, and the plus is the other side. So you can draw it like that, okay? So plus on the long line and negative on the small line. And of course, little cells can be put together, plus against minus, as many as you want. The more you put, the more voltage you can get. And so typically a cell, a battery, sometimes consists of many cells. A battery can be one cell, or it can be many cells put together, right? And so the most important thing for us to remember, though, is that batteries and cells are what we call voltage sources. They provide voltage. Remember, we talked about that. So in the circuit, we often represent the voltage source like this with what looks like a battery. Then we represent the conductors, and wherever possible, we draw the conductors as straight lines instead of curvy lines. And then we would have a load. Now, the loads have a whole bunch of different symbols. So let's put a load here. Let's put a light bulb, which is a wiggle with a circle around it, or something close to that. And you remember that in grade 9, right? That's a light bulb. Light bulb. When we're finished this video, part of your assignment is going to be to go on the internet and to research some of the different symbols that we use. And you'll find all kinds of them. The symbol for a meter, a voltmeter. The symbol for a motor is often a circle with two little bars on it. Looks like a little alien with an M inside. And of course, unfortunately, they're not all the same. A generator is a G with two little bars on the side, and the wire attaches like that. So there are many different symbols. You learn a lot of them in grade 9. You'll have to refresh your memory, and we'll deal with those shortly. However, to deal with the circuits themselves, because the load can be anything, right? What I like to do is I like to use the symbol for a resistance. Because, of course, a load, right, is a resistance. So I'm going to take out my light bulb, and I'm going to take this out here, and I'm going to show you, if you didn't learn this in grade 9, the symbol for a resistor or a resistance is a little jagged little mountain. One, like that. That just means any load. That's what I refer to that as. Any kind of load at all. So to save time and effort, that's usually what I do on my circuits. So we have our voltage source, which in this case is the group of cells here. Now, you could also have a generator as a voltage source. You could also have a variable voltage source, and we'll talk about all those later. And then I have my load over here. And I have my conductor, which is the wire that's conducting them together. And so on the battery, it's helpful too, for now, to remember that the long side is plus and the short side is minus. Okay? This would be wrong. You can't draw a battery like this, because it has two long sides. You see, this end is plus and this end is plus. That won't work. It's always long, short, long, short, long, short. They come in pairs. So there's always a negative side and a positive side. And of course, what would happen then is electrons would flow from the negative side around through the circuit. They would go through the load, and they would come through here. As they go through the load, that's when they do work. They make something happen, and that's the whole point of the circuit, right? Okay, now, you'll recall in grade 9 that there are two different types of circuits depending on how the electricity can flow. So, two types of circuits. One is called a series circuit. Let's talk about what series means. Series means that the basic way to think about a series circuit is there is only one path. Through all loads for the electrons to follow. There's only one path, through all the loads, because it's not one path through every load. It's one path for the entire circuit, and all the loads are all on the same path, right? There's only one way to go. And I'll draw you an example of what that might look like. Here is a voltage source. Here is a conductor, and I'm going to put 3 loads, and I'll just use the general signal sign here for a resistor or resistance of some kind. Here is a circuit with 3 loads on it. One might be a light bulb, one might be a motor, and one might be a heater. Who knows, whatever they are. Load 1, load 2, and load 3. And of course, this is our voltage source. If you were electrons, you would find your way, you would find that the path of the electrons is in a circular flow through load 3, through load 2, through load 1, and back up here to the positive side of the battery. And that's the only way you can go. The entire current of electrons must flow through load 3. And then the entire current must flow through load 2, and the entire current must continue through load 1. So that's what we mean when we say that there's only one path to get from this side of the battery to this side. The only way to do it is to go through the entire series circuit. So the loads are in series. I'm going to write that. The loads, it says loads, it looks like an A. The loads are in series. And a series is just a fancy word for like a string or a line, right? The loads are connected in series. Now, what would the other type of circuit look like? Well, if you recall, you'll remember, you can also connect your loads like this, where you have a wire and a conductor, and here's one load right here. Now, the electricity will flow through here, and it would get to here, and it would go up through this, and it would go around. So there's nothing special about that. But if I add wires like this, and I put another load like this, then what happens is the electricity, when it gets to this spot right here, some of it goes up, but some of it continues along. So the current splits up. It's like a crowd. Imagine a crowd of people. Some of them would turn and go to the right or to the left, that would be going to the left, and the others would continue on and they would go up through here. And they would go through this load and they would come back and join up. But you notice how they never went through load number 1. Let's call this load number 1. Some of the electrons went through load number 2 and some went through load number 1, but everybody didn't have to go through both. And I could add another. And by adding load number 3 now, some of the electrons that were traveling here might turn left and go up, but some would continue on. So the crowd keeps getting smaller, doesn't it? And they would go up and around, and they would come back and join up here and make their way all the way back to the battery. So you see what happens is here and here, the crowd of electrons, or the current, is split. The current is split up or divided. So this might be an interesting way to connect stuff, but you have to be careful because the amount of current that you're going to get flowing is going to be different. Whereas here, every load got the same current in every load, right? So if you're designing an electric circuit, that's important. The same current in every load, whereas down here, the current splits up. Splits up, I guess we could say, between the loads. All right. And of course, this second type of circuit has a name. It's called a parallel circuit. I suppose I should have written that first. I'll write it at the bottom here. It's called a parallel circuit because you can see how the loads are sort of lined up parallel to each other. Parallel circuit. And the way you can sort of define this is that there are more. I guess you have to say there is. more than one path for electrons to follow. That's another way to think of a parallel circuit. Or you could also think of it as current splits up between the loads, which means that not everybody goes through every load. All right, so that's the basic difference. Now we've drawn two very simple pictures. They don't have to actually look like what we have on the board or on your notes here. But these are generally the way when we're learning, we first start to depict them. The series circuit, here one path, and the parallel circuit down here, several different paths. All right, now the last thing we have to do is we have to talk about the mathematics associated with each type of circuit. So there's a fellow by the name of Kirchoff who came up with some rules and laws that talk about the relationship between voltage and current and resistance in each circuit. So we need to do that as well. And then we'll be able to actually solve the circuit. So Kirchoffs Laws for electric circuits. Basically, here's what Kirchoff said. He said, if you take a series circuit, then the voltage, the total voltage provided by the source, right, will be used up by all the loads along the circuit. In other words, that force or that amount of pushing is going to be sort of, used up, or it's going to be absorbed by these loads. So the voltage across load number 1 plus the voltage across load number 2 plus the voltage across load number 3 plus the voltage on load number 4 and load number 5 and load number 6 and load number 7 and load number whatever. We use a little n. So this can go on. All of the voltages at each of those loads must add up to the total voltage of the circuit. Okay? Then he said that the current that flows, and we've already mentioned this, the total current produced by the circuit, all of it will flow through load number 1. All of it, the currents will be the same for load number 2. It'll be the same. Oh, look at me, I'm putting pluses instead of the same. Sorry, I'm going to fix that right off the bat. The same, equals. The currents are always equal everywhere you look in this circuit. And that would go on until you reach the very last one. Whether you had 3, 5, 10, 5,000, 6 million, whatever, how many loads you had on the circuit, they would all be equal. And of course that little dot doesn't mean anything there. Let's get rid of him there. The last thing he noticed is that the total resistance of the circuit, right, so that was the total current flows through each and every load equally. Then he said that the resistance, the total amount of resistance by the combination of all the loads together resisting the flow of electrons would be equal to the resistance of one load plus the resistance of the second load. And again, we would add them all up until we were finished, until all of the loads were added in. And that would be the total resistance of the circuit. Kirchoffs Laws for series circuit. Voltages are added, the current is the same at each load, and the resistances are added at each load to give us the totals. Then he said, what about a parallel circuit? Well, a parallel circuit kind of works differently. Okay, let's go back and look at the two pictures to see the difference. In the first series circuit, we said voltages are added up. Voltage is kind of like the desire of the electrons to move. It's what's pushing them. But if electrons are following this path, I'm going to use a different color this time. When they get to this load, some of their desire to move, or some of the energy that they have, is going to be taken away by this load, whatever it's doing. Remember we said the work that gets done by the load is the moving electrons. So when they leave here, they're going to have a little bit less energy. So what we say is there's a voltage drop. Right? It's kind of like if you had a bunch of energy and then you had to run up a hill. Okay, so let's now go down to the parallel circuit. That's a little too far. Right about there. Let's look at what happens with the series and parallel circuit. In the parallel circuit, that voltage, well, let's finish here. The voltage is going around and a little bit gets lost. So I said it's like if you were going for a walk and you had lots of energy. Well, if you went up a little hill, like load number 3, afterwards you'd have a little less energy. And then if you went up another hill, like load number 2, your energy would keep getting sort of sucked away from you. So each of these loads represents sort of a drop in your energy, right, as you go through. Well, when you look at the parallel circuit, it's not going to add up because you don't have to go up all 3 hills. So the voltage that's pushing you this way is the same amount of energy pushing you across this guy, which is pushing you across this guy. The difference between this side of the circuit and this side of the circuit is the voltage provided by the voltage source. So the voltages through each load are the same. The amount of voltage that's being pushed across each load is the same. So what we say in parallel is that voltage total is the same at load 1. Whoops, I'll do it again. It's the same at load 1, and it's the same at load 2, the same at load 3, and the same all the way up until you get to your very last load, whatever number that is. So the total voltage is the same across each load in a parallel circuit. Now let's go back and look at the current. In the series circuit, the current went through every load, so it's the same amount of current going through each load. And I've drawn the lines there. Okay, so what I guess I should have drawn here was the word drop. I forgot that. The voltage drop, right, which talks about how much the energy has been dropped. But now the current is going through. So let me erase some of these arrows because they're getting confusing and there's too many of them. Let's look at the current. The red line that I drew represented the current as it's going through this circuit. So let's just think about it. All of the current leaves the battery. It all goes through load 3. It all goes through load 2. It all goes through load 1, and it all ends up back at the battery. And so wherever you measure the crowd, you're going to get the entire crowd of electrons passing through. But here, we talked about how the electricity splits up, right here and here. The current divides. So you have a different amount of electricity. But if you add up all the electricity going through here, plus the electricity through here, plus the electric current through here, those 3 will add up to the entire crowd of electrons, or the whole current. And so, for parallel, for Kirchoffs laws, we have that the current is added. The total current, IT for total current, is equal to the current flowing through load 1 plus the current flowing through load 2 plus the current flowing through load 3 plus the current flowing through all the loads until you get to the very last one, N. All right. Now the hardest one to get our head around is the resistance. The series circuit is easy. The resistance is what's stopping you. And so if you were going for a walk around this series circuit here, well, all 3 loads are stopping you. And if you add up the resistance of each load, that's the total resistance you would face as you go around your walk through the circuit. But on the parallel circuit, it's a little bit different. All right? Now, again, it's looking pretty crazy here, so you know what I'll do? I'm going to go down to the bottom and draw another parallel circuit really quickly, because it's too hard to use that. So here we do a little circuit, and we'll put our 3 loads here like this, just quick, so it looks the same. Drawing this really sloppy, that's okay, you get the idea. Let's look at what the current is trying to do. The electric current is leaving the battery, and it's trying to go from here, and it's trying to get over here. And there are 3 ways it can do that. Some of it can go this way, some of it can go through here, and some of it can go through here. So imagine a crowd of people, and they're all standing right here. Big crowd of people, hundreds of them. and they have to get going because they're being chased by, Godzilla. There's Godzilla and his big teeth, and he's chasing them, his little puny arms. So they're trying to get away, and the safety is to get across to the other side of the circuit. Well, some of the people will run this way, some will run up here, and some will run here. If I add another place for them to go, even if it's not a very good one, that gives the people an extra path, an extra place to go, so that more of the crowd can get across easier. The more loads I add to the circuit, the more extra paths I give the people to run and get away from Godzilla. So what happens is when you add resistances to a parallel circuit, the overall resistance actually goes down. It actually gets easier and easier for the electrons to travel from one side of the circuit over here to the other side here, because now they have more paths to follow. So adding resistance in parallel decreases the total resistance of the circuit. Kind of seems backwards to what you would think. But it's because you're opening up a new path each time, and that makes it easier. All right? So what I'm going to do is just erase that picture. Now we have to figure out, how do we describe that mathematically? How do we show that adding a resistance, how do you show that adding 2 things or 3 things or 4 things will actually give you a smaller and smaller number? Well, you do it like this. You do it with reciprocals. 1 over the total resistance equals 1 over the resistance of one load plus the resistance, 1 over the resistance of the second load plus 1 over the resistance of the third load plus whatever you do, you just keep on going until you get to the very last resistance of the loads. This is a reciprocal relationship. All right? Now, unfortunately, when you write it this way, this is what you get. You don't get the total resistance, you get 1 over the total resistance. So if you were to add all these guys up over here and get an answer, that answer is 1 over the total resistance. So you have to remember to sort of take the reciprocal of that at the end. And I'm going to show you an example of how that would work. So there's Kirchoffs laws for parallels and series. Okay? In series, voltages are added, current is the same at every load, and resistances of each load are added. In parallel, voltages across each load are the same. They are equal. The currents are split up, and so they add up to the total. And the resistance adds up in a funny way as reciprocals, because when you add more resistance in a parallel circuit, you add more pathways, making the total resistance go down. In the next video, we will actually do some examples, but that's enough for today, or for this little session, and then you can take a break and watch the next video when you're ready, or maybe even watch this one again if you're not quite sure. But I hope you remember a lot of this from grade 9.